Hey guys, Kenny here again. So today we're going to go ahead and take a look at chaos, uncertainty, and Brownian motion. This is part of our unit on matter and thermodynamics. And so I think this is our chance to go ahead and start looking a little bit at quantum mechanics and begin to kind of take a look at how patterns and predictability is a part of science and what that means for things that seem unpredictable. Okay, so we're going to take a quick look at this idea of chaos theory. And you may have heard of the butterfly effect before, and we'll reference that as we go ahead and go through our presentation today. But make sure you understand the key vocabulary. That's really the big takeaways for today. The rest of this gets a little bit difficult and challenging, and so it's okay if you struggle with a little bit of it. As if you go on to take, if you go to take more of this in college, you'll get to talk about it in more detail. All right, so let's jump in with our essential questions. So, number one, what is chaos theory and how does that relate to the butterfly effect? Okay, many of you have heard of the butterfly effect. There was even a movie with Ashton Kutcher all about it. But what does that actually mean in terms of something that's related to physics? Number two, what is Heisenberg's uncertainty principle? This is a cool topic that relates to quantum mechanics. We want to know where it actually came from first and how we currently use it, and how we use it in common parlance may be a little bit different from how we use it specifically for physics. Then we take a look at what is emergence and how does this relate to the idea of chaos and chaos theory. And lastly, we'll finish up with this idea of Brownian motion and how that relates to chaos theory. So let's go ahead and jump right in. Now, first thing I want to remind you of is our laws of thermodynamics we introduced to you. So the first law of thermodynamics states that energy can be changed from one form to another, but it cannot be created or destroyed. So the total amount of energy and matter in the universe will remain constant, merely changing from one form to another. The second law of thermodynamics states that the disorder of an isolated system is not in equilibrium will tend to increase over time, approaching a maximum value at equilibrium. And then the third law of thermodynamics says that as temperature approaches absolute zero, the entropy of a system approaches a constant minimum. Now, one of the things we've introduced you to is this concept of entropy. And understanding what that means is going to play a key role in us really being able to understand these things coming up. Okay. Now, some other key words when we start looking at this idea of equilibrium. Equilibrium is going to play a key role too, and it relates to what we talked about in terms of entropy. Okay. So we typically talk about entropy in terms of like chaos or disorder. But in reality, entropy is the movement of a system towards this idea of heat or thermal equilibrium, where all the energy is spread out evenly everywhere in the universe. We even talked a little bit about how this relates to the big freeze or big chill, one of the omega points for the end of the universe. Okay, so let's take a look at chaos theory. Now, chaos theory declares that tiny changes in circumstances can have major ramifications later on. And this should have some sort of inkling in the back of your mind in terms of connecting with what we call the butterfly effect. Let's say if you leave your house 30 seconds late, then even though you just missed your bus, you may have to meet someone who directed you to a new job, and that new job changes the path of your life forever. Small changes in normal sequence of circumstances can cause major changes or shifts in the outcomes overall. Now, chaos theory applies most famously to the weather, where tiny wind eddies can seed a hurricane on the other side of the planet, and this is the origination of this idea of the butterfly effect. Now, one butterfly flapping its wings is not actually big enough to cause the production of a hurricane. But the idea that small changes in a set of parameters can change larger outcomes is definitely something we've seen in science. But in reality, the chaos in chaos theory is not actually chaotic in the literal sense. because patterns begin to emerge from it, and we start realizing that what seems chaotic actually has a set of parameters that determine that the likelihood of this event occurring is possible. Now, we may not understand all of those parameters or be able to quantify them in a meaningful way to simulate things like this in a computer, but we're getting better at it every day. And so, what we're looking at is the process of developing predictive systems based on the data that we know about that particular system. And again, I keep using this term system. System versus surroundings is a big idea, and this is where that whole thing about frame of reference comes into play when we go ahead and talk about a lot of the things we've discussed here in physics so far. All right, so I have a little video that's going to go ahead and talk about this, and I think these guys do a pretty good job, so I'm going to let them give you an idea of how this plays out, and then we'll come back and talk about it again.
So practice. Oh, first piece of cake. That's what I wasn't trying to do. I was trying not to pot the ball.
The butterfly effect really is used as a paradigm of chaos, the idea that perhaps a butterfly flapping its wings in July in New York can determine whether or not it snows in Nottingham in December. So that tiny, tiny change amplifies through the weather systems. It's an overstated example, that's for sure. I mean, in reality, it would make no difference because all of the other perturbations, the wind, the waves, the ripples, aeroplanes coming across would be far more significant. But the concept that some systems are so sensitive as to be essentially unpredictable is very real. And the interesting thing there is that really simple systems show this. Many simple systems show this behavior.
When I hit the reds with this cue ball, now I may not be good enough to actually hit them, but the point I want to make here is the configuration of the reds after I hit them with the cue ball is in a sense a demonstration of chaotic motion. Well, that wasn't very good. That was a pretty boring thing to do. Yeah, you have a go and I'll hold the camera. You see, the reason I've tempted you down here to do this is for once we get you on camera and we guys can have a good laugh at you rather than the other way around.
So what this is a system, it's a double pendulum. The idea is to show that even a really simple system like a pendulum that's so regular, of course, it's been used to make clocks for 100 years or so. If you take two of them and couple them together and give them enough energy, those pendulums can lose completely their regular behavior and behave completely erratically, chaotically.
Now, Brady, what I want you to try to do using your semi-professional skills as a snooker player is to hit the front ball there. Oh yeah, sure, I've forgotten I'm the cameraman. Okay, yeah, okay, go, wait a minute, I'll move it, I'm waiting for it now. Go. Oh, that's much better. Now, look at that configuration. We'll try to remember where all these balls have gone. In particular, let's look at them up at that far end of the table there. Now, go on, Brady, put them all back again, and we'll compare the positions. I'll pay you £100 if you can repeat that condition. No, I'll pay you £1 million if you can repeat that condition. Yep. Good, well done. So hit that front ball again as close as you can to the previous position with the same speed, and then let's just look at the conditions this time. Okay, fire. There you are, you see, the condition is completely different. And up there, you potted the red. Yeah, you potted the red up there, which you didn't do before. So I saved my £1 million, you see.
Here's one pendulum, of course, very predictable, very regular. If we set the thing in motion with quite a low energy, so we lift them slowly, you can see that's also quite regular. The two arms are kind of vibrating against one another all the time. If I lift that right up in the air and then let it go, you can see the system's moving like crazy. Oh, there it's got a load of energy and it's away. So you can see that there's a big change of energy between the lower pendulum and the upper pendulum, and it's meaning that the tips of those penduli are moving in very different ways. And if you track out the motion of the tips of those penduli, you'll see that they fill space pretty much uniformly. So rather than just rocking backwards and forwards along a single arc, they're flying around in a completely erratic way. So just the very fact of having two of these penduli coupled together, two different pivot points, changes completely the long-term behavior of that system. even any tiny change away from those initial conditions will eventually produce completely uncorrelated behaviour. In fact, if you do this with a computer simulation, you set the two of them off and perhaps change the start speed by 1 part in, say, 10 million. After only 3 or 4 swings, the motion's completely separate. So that kind of sensitivity to initial condition really shows through quite quickly.
But if the computer simulation can crunch it when you put the initial conditions in, it's not chaotic, is it though? It's just different conditions produce different...
That's right, that's right. So the laws that determine how these things move are really simple. Essentially F equals ma, just Newton's second law. So what's going into that, the maths is really simple. However, the trajectories that produces depend so sensitively to how you set it in motion that the overall picture is very, very messy and very chaotic looking.
That's a demonstration of the sensitivity of this problem. This is a many-body problem, lots of billiard balls here. It's the sensitivity to the initial conditions. If you just deviate the point at which you hit that front red by a little bit, or just change the speed at which it's hitting, you get a totally different configuration. It's become a very complex problem.
Professor, can I ask you this though? You said it's very complex, but if I gave you enough parameters and enough computing power...
Great question. Now this brings us on to the question of things like the weather. And you're right, if we could precisely locate all the positions of the reds inside the triangle, we take the triangle off of course, and then locate the starting position of your ball and the direction in which it's going and the speed with which it's going, and find out exactly where it hits that front ball, then in principle we could do a pretty good job at predicting the motions. But we find that we can only specify those things to so many significant figures, those numbers to so many significant figures. And if you start changing those significant figures by a small amount, the effect, the change in the pattern is amplified very, very strongly. And of course, this is very similar to the problem of predicting the weather. You can predict you know the velocities of all the wind patterns, say in the Atlantic, and the pressures and so on, to a reasonable degree of accuracy, say a couple of %. And that's great for doing weather forecasting for a couple of days. Or maybe a week if you're lucky. But trying to predict the weather 6 months from now, or even 1 month from now, is much more tricky. And a similar thing is operating for these balls. Very, very sensitive to how you hit that front ball.
Usually in a chaotic system, you can write down very simply the equations of motion. So you really understand the physics, you understand the forces that are setting the system in motion, you understand how to write down Newton's laws or alternative formalisms to Newton's laws that tell you how the system will evolve. So you understand that. But the problem is that if those laws are such that the system's got several ways in which it can move, so in this case there's 2 ways in which the system can move. We've got the displacement of that pendulum and the displacement of that pendulum. If the number of things that's keeping that system constrained is equal to the number of motions it can have, then it behaves regularly. But if you start to take constraints away from the system, then that allows the thing to evolve in a chaotic way. So all it is in terms of whether a system is chaotic or not, is it free to become chaotic? If it is, it will do.
The key point about playing snooker, of course, is that there's friction. This ball will not go on forever. So I want to make the very drastic assumption that we're going to neglect friction. So I want you to imagine that this ball, rather than slowing down, just has no dissipation. It can just carry on forever without losing momentum. So let's try this. Now, the other key feature with this, as you see, is that the ball bounces, not quite, but more or less with specular reflection. Specular means it behaves like light hitting and reflecting off a mirror, where the angle of incidence is equal to the angle of reflection. Because the sides of the table, these 2 sides are parallel, and these 2 sides are parallel, we've got a rectangle here. It means that the motion that we have when we let this frictionless ball go, the motion is not chaotic, it's regular. So before I describe what a chaotic stadium is, first of all I want to show you what a regular stadium is. So let's do it again. We hit this thing really hard, and we've got our specular reflection, and this thing will carry on going. And we can write down a very simple equation to describe that motion.
So this is something that's been sitting in my dad's shed for 2 or 3 years, and we used to amuse the children with it. It's a sprinkler for the garden. So you put your hose on the bottom and it squirts up here, it squirts through this flowing thing. And what happens is it flies around all over the place and flicks water. You see a few bits coming out of it, so it flicks water all over. And rather than a circular sprinkler just watering part of your lawn or part of your flower bed, this flicks water all over the place, so everything gets completely soaked. But the principle of it is really the same as this double pendulum. It's another double pendulum system. We've got one pivot here for this tube, another one here for the flower head, and so the motion's really the same as the double pendulum. And the fact that the 2 of them can flick around all over and spray water around all over the place means that you can very easily and efficiently water your garden. If you really want to get something random, just take 2 very simple systems and let them talk to one another and communicate with one another via this pipe. That's perhaps the strange thing, that it really is that taking 2 things that are so simple, how simple as you can make it, and letting them interact, produces something that's unpredictable, but in this case, useful and quite quickly, I guess.
We can start our ball here and set it off. And why is this thing so regular? Well, the ball hits, and this angle is equal to that angle. We're assuming there's no friction, we're assuming elastic property, carries on in a straight line. It then bounces in a very predictable way. It comes back again. Now, here's a stadium, the Brownian Stadium, where these rules don't apply. It's a very easy thing to construct. It's just a couple of semicircles, two rectangle sides. So instead of these flat edges here and here, and parallel edges, we keep these side ones parallel to each other. We have curly bits there. Now, immediately we see there are two interesting types of orbit. Clearly, a trajectory like that, where the ball just bounces back and forth here, is very boring. And also, this one, back and forth here, is completely predictable. And I can also devise another type of motion. Let me see if I can draw it here. I can do this one. If I just get that diamond one right, that is simple and is completely stable. However, there's another class of trajectories where things get much more complicated. If I just do some general trajectory where I start, say, here, off the mid position, and go around here, then with specular reflection I can do this following my simple rules. And you can see now it's beginning to look a bit interesting now. What's going to happen? I've got to do that specularly. So it's going to come over here and then go up there and there. Now what's it going to do? It's going to come back here. So if you start doing this, this motion just goes on forever. It never reproduces. Path is far from periodic. And in particular, if I just change this trajectory by a little bit, then I'll end up very quickly getting an orbit that's much different from the one when I started off by sending the particle this way. So huge sensitivity to initial conditions. No, too hard for me.
Okay, so the sensitivity to these initial conditions that makes something appear chaotic. Now, in these examples, they're using a limited number of particles or a limited number of pieces on a pendulum. Now, in terms of the kinetic molecular theory and all of the atoms involved or all the molecules involved, we're dealing with huge numbers. Okay, if you're taking chemistry, think about moles, right? But we're looking at enormous numbers of molecules. And so it is much harder to predict the outcomes of these systems because we don't know all the parameters for the initial conditions, which makes it very difficult. And it's cool in these examples because it ties back to what we talked about last term in terms of things like momentum, in terms of things like angle of incidence equals angle of reflection, which we'll talk about later this term when we start looking at lenses. Okay, a lot of things that kind of fit together in terms of physics. But this idea that small changes in the initial parameters can have large outcomes in terms of the differences in the way the system behaves creates this idea of chaos theory, this idea of the butterfly effect, this idea of uncertainty, which brings us to our next topic. And that is what's known as Heisenberg's uncertainty principle. Now, Heisenberg's uncertainty principle states that the speed or momentum and position of a particle at any instant cannot both be known exactly. Okay? The more precisely you measure one, let's say the speed or velocity, the harder it is to identify the position. The more accurately you measure the position, the more difficult it becomes to measure the velocity. So Werner Heisenberg argued that the very act of observing a particle changes it, therefore making precise knowledge impossible. So neither the past nor future behavior of any subatomic particle, so remember your protons, neutrons, electrons that we've talked about, can be predicted with any sort of certainty. And so we use this term a lot to talk about the fact that things are kind of unclear, but I think the video that I'm going to show you here will give you a much better understanding of how the Heisenberg uncertainty principle works in physics and how we have kind of adopted and used it in other areas. So let's go ahead and take a watch of this video, and then we can talk a little bit about it.
The Heisenberg uncertainty principle is one of a handful of ideas from quantum physics to expand into general pop culture. It says that you can never simultaneously know the exact position and the exact speed of an object, and shows up as a metaphor in everything from literary criticism to sports commentary. Uncertainty is often explained as a result of measurement, that the act of measuring an object's position changes its speed, or vice versa. The real origin is much deeper and more amazing. The uncertainty principle exists because everything in the universe behaves like both a particle and a wave at the same time. In quantum mechanics, the exact position and exact speed of an object have no meaning. To understand this, we need to think about what it means to behave like a particle, or a wave. Particles, by definition, exist in a single place at any instant in time. We can represent this by a graph showing the probability of finding the object at a particular place, which looks like a spike, 100% at one specific position, and 0 everywhere else. Waves, on the other hand, are disturbances spread out in space, like ripples covering the surface of a pond. We can clearly identify features of the wave pattern as a whole, most importantly, its wavelength, which is the distance between two neighboring peaks, or two neighboring valleys. But we can't assign it a single position. It has a good probability of being in lots of different places. Wavelength is essential for quantum physics because an object's wavelength is related to its momentum, mass times velocity. A fast-moving object has lots of momentum, which corresponds to a very short wavelength. A heavy object has lots of momentum even if it's not moving very fast, which again means a very short wavelength. This is why we don't notice the wave nature of everyday objects. If you toss a baseball up in the air, its wavelength is a billionth of a trillionth of a trillionth of a meter, far too tiny to ever detect. Small things, like atoms or electrons, though, can have wavelengths big enough to measure in physics experiments. So if we have a pure wave, we can measure its wavelength and thus its momentum, but it has no position. We can know a particle's position very well, but it doesn't have a wavelength, so we don't know its momentum. To get a particle with both position and momentum, we need to mix the two pictures to make a graph that has waves, but only in a small area. How can we do this? By combining waves with different wavelengths, which means giving our quantum object some possibility of having different momenta. When we add two waves, we find that there are places where the peaks line up, making a bigger wave, and other places where the peaks of one fill in the valleys of the other. The result has regions where we see waves separated by regions of nothing at all. If we add a third wave, the regions where the waves cancel out get bigger, a fourth and they get bigger still, with the wavy regions becoming narrower. If we keep adding waves, we can make a wave packet with a clear wavelength in one small region. That's a quantum object with both wave and particle nature. But to accomplish this, we had to lose certainty about both position and momentum. The position isn't restricted to a single point. There's a good probability of finding it within some range of the center of the wave packet. And we made the wave packet by adding lots of waves, which means there's some probability of finding it with a momentum corresponding to any one of those. Both position and momentum are now uncertain, and the uncertainties are connected. If you want to reduce the position uncertainty by making a smaller wave packet, you need to add more waves, which means a bigger momentum uncertainty. If you want to know the momentum better, you need a bigger wave packet, which means a bigger position uncertainty. That's the Heisenberg uncertainty principle, first stated by German physicist Werner Heisenberg back in 1927. This uncertainty isn't a matter of measuring well or badly, but an inevitable result of combining particle and wave nature. The uncertainty principle isn't just a practical limit on measurement. It's a limit on what properties an object can have, built into the fundamental structure of the universe itself.
Okay, so physics can be weird. Okay. Now, there's another concept that I would like to introduce you to that relates a little less to the Heisenberg and a little bit more to this concept of chaos theory, and that is what we call emergence. Now, emergence is this idea that if we go ahead and start looking at a system, especially complex systems, larger entities are built up of smaller parts. And when you combine these smaller parts together, they begin to develop this greater set of abilities that does not reflect the smaller parts. Okay. The simplest example of this is to look at something like water. We're all familiar with water. We deal with water on a regular basis. We're mostly made up of water. But what is water made up of? Well, water is made up of hydrogen and oxygen, which is made up of its protons, neutrons, and electrons, and so on and so forth. But hydrogen is incredibly flammable. Oxygen is needed for fire to burn. But if you combine the two together, they create water, which puts out fire. This is a new property that emerged from the combination of the two simpler atoms. Okay? So this concept is really valuable in terms of trying to study complex or difficult systems. So life is a great example of this. You are an emergent property. You are able to fight against, the process towards equilibrium as your body wants to decay into uniformity. Okay, as your energy gets spread out into the universe. Now, we are able to fight that off through food, through sleep, as our body goes through its normal processes. Life is an emergent property. You are you not because of everything that makes you up, but because everything that makes you up working together creates you. And that may seem a little counterintuitive, but if I were to go ahead and take one cell from you, is that you? Well, it doesn't behave like you do. It has some of the properties of you, but it doesn't add up to you. And so we have to think about all those different cells. Well, but interestingly enough, all those cells were built from essentially exact same DNA. But certain parts get turned on, certain parts get turned off. This becomes a liver cell, that becomes a brain cell, that becomes a lung cell, and so on and so forth. And all those things need to be sustained through food, exercise, sleep, these types of things. Otherwise, they start to break down and decay. And in fact, when you die, all the material, all the matter that makes you up, all the energy that is stored within inside your body dissipates and moves back into the environment around you. So, this concept of emergence is that simple things end up going ahead and producing patterns that emerge very differently from what we originally talked about. Now, there's an example that I was given years ago that I still like to refer to. It's an oversimplification in many respects, but I'm going to go ahead and use it here to kind of try and illustrate. If we go ahead and create a maze, and that maze has different options, okay? When we start to take a look at that maze and realize that it's got all these different pathways that can go ahead and lead to different outcomes, but there's only still one outcome that's eventually going to lead to the exit, we start to realize that how would anybody get through this without testing it or trying out the maze? And in many respects, you can't. But you also might think, well, how does this relate to intelligence? Now, if we were to think about something like a slime mold, we don't typically think of slime molds as being very intelligent. In fact, we think of them as being kind of the opposite and not being very intelligent. But a slime mold can find its way through a maze. If you were to go ahead and put food on one side, you begin to realize that the slime mold is going to check every single pathway and that those pathways can go ahead and lead towards the ending or not. Now, it's not that the slime mold is smart enough to solve the maze, it's that the slime mold tries every possible outcome. So the slime mold comes into the maze. Let's call this the start. This is where we put the slime mold. And on the other side, we have food. Yay! Okay. It's not going to go ahead and just know the path, although I'm going to go ahead and draw it like it does. But by using this, it got to this point because every branch that it had, it explored. It threw out parts of itself to go ahead and explore every single potential outcome. But when it gets to those endpoints, and those endpoints don't provide any sustenance or food or some needed material, what it does is it then goes ahead and kills those off. So these other pathways end up being destroyed or shut down because they don't provide something useful. Okay. to the organism that's searching for it. Now, is that intelligence? It's not intelligence in the same way, but it is sort of an intelligence that it's trying all these different pathways, and it only keeps going those pathways which provide it with some benefit or sustenance. We can use these types of modeling behaviors to go ahead and describe things from gravitation to, we'll talk about electromagnetism and the electrical force as we go ahead and go on. But emergence is the production of these new properties due to the interaction of simpler things, which should again kind of click with what we've been talking about in terms of chaos. So I have a quick video here. Well, actually, this one's not super quick. And instead of actually watching it, I'll go ahead and attach it separately so that you go and watch this idea of complexity of emergent systems show up. And then the last thing I wanted to talk about is this concept of Brownian motion. Now, we can actually see vibrations and movement of particles. We can track particles. And this relates a lot to what we've been talking about in terms of the kinetic molecular theory. First identified by botanist Robert Brown, he's noticed the twitching of pollen particles on his wet microscope slide, but it was Einstein who actually described mathematically how they worked. Now, Brownian motion explains how pollution diffuses through still air or water and describes many random processes from floods to the stock market. It's very unpredictable, and it's related to both chaos theory and it's related to this idea of emergence. So what we begin to see is that, again, if you know enough parameters, you could predict this, but you start seeing a particle that runs into another particle and it changes its course and until it runs into something else and then it moves. And the pattern on the right reflects the trajectory or travel course of that particle. That looks very chaotic and very hard to predict. But we can go ahead and do that if we know all of the parameters and what it's going to go ahead and run into. So I have a short little video to watch and we'll call it good for today.
Water can exist in 3 different states. In the iceberg, it's solid. In the sea, it's a liquid. In the surrounding air, it's a gas. Solid, liquid, and gas are the 3 states of matter. Solids have a definite shape. A block of ice takes the shape of its mold. As it melts, it changes. The water spreads out and fills up the container. All liquids behave this way. They flow and find their own level. Gases spread out even more, filling any space available. The way solids, liquids and gases behave gives us clues about how their particles are arranged. In solids, the particles are in a fixed framework. They're held close together and vibrate. In liquids, the particles are still in contact, but this time they're free to move around. The particles in a gas are far apart. They move quickly and randomly in any direction. But how do we know the particles in a gas behave this way? Some of the evidence comes from looking at how smoke appears under a microscope. Smoke from a straw is injected into a small container. A lid keeps it in place, and a bright light enables it to be viewed under a microscope. It looks like tiny jittering points of light. When a straw burns, the smoke produced is mostly bits of carbon which haven't combusted. Under a microscope, they catch the light and appear to glimmer. But why do they randomly dance around? The movement of the smoke is caused by collisions with invisible air particles. As the air particles move about, they knock the smoke first this way, then that. Particles in a gas move randomly and quickly. Flowers produce pollen, which is a very fine dust, easily brushed off by a finger. Nearly 200 years ago, it was this dust which first gave us clues about how particles behave in a liquid. In the 1820s, the botanist Robert Brown was carrying out a study of pollen grains. He decided to crush the pollen and suspend the grains in water. But to his annoyance, the pollen continually jittered around. Today, we can best see this effect by looking at tiny carbon particles instead. A drop of carbon powder suspended in oil is placed on a slide and viewed under a microscope. Just like the smoke, the carbon is dancing around. Brown didn't know why this movement occurred, but we now believe it's caused by the motion of particles in the liquid. The carbon is being pushed around by collisions in the oil.
Okay, so you can see here that the kinetic molecular theory model is a good one in terms of the movement of particles, but it's a fairly complex system, and so making mathematical predictions about how things are going to move or behave is difficult. And if you remember your biology days, we talked about this idea with respect to things like diffusion. Particles tend to move towards equilibrium, right? And so this relates to our laws of thermodynamics and the ultimate potential end of the universe as you increase entropy. Again, we typically talk about it as disorder, but in actuality, it's an ordered process that just has very complex play out of variables. And if we knew enough of the initial conditions, we could probably create a model to go ahead and explain this. But when you see patterns like you have here on the right, you talk about the jittering of pollen grains or smoke particles, which is the unburnt carbon. You're dealing with the fact that they're moving because of collisions with other particles. This is at the core of what we kind of talk about in terms of chaos theory, where small, subtle changes to those parameters change the outcomes. And this relates to the concept of emergence, whether we're dealing with you, the new properties of molecules. And this all relates to everything from how temperature works, because how temperature is transmitted is related to the size and number of particles, the specific heat of molecules, depending on how big the molecule is that we're dealing with. All of these things are related to each other. And their basis is actually at a quantum level, which is how we start tying in things like Heisenberg's uncertainty principle. All right, guys, hope you got something beneficial out of this. Take care of yourselves, stay healthy, stay safe, and we'll talk to you soon. So long.